All right, so here's our problem. After a snowstorm, a boy and girl decide to have a snowball fight. The girl uses a large slingshot to shoot snowballs at the boy. Now assume that the girl fires each snowball at an angle from the ground, and the snowballs travel with an initial velocity of v0. First of all, it's a big paragraph, and oftentimes my students get absolutely overwhelmed that it's such a big paragraph. So the very first step is to change the representation. What does she mean by change the representation? That wasn't in my textbook. Okay, change the representation means draw a picture. Now, if you notice, everything that was in that big ugly paragraph before, I've represented in the picture. Here's the snowball. This girl, she has we can't really tell, she has a little scowl on her face, an evil grin. She is about to shoot this snowball at this angle with this initial velocity. Now remember, vectors are just representations of the velocity at that moment. That initial velocity is going up at this angle. The snowball trajectory, how that snowball is actually going to travel. Now you may be thinking, well, Ms. First, we do not have a question. That's right. Don't even think about what the question is. You have to understand the problem before you get to the question. Now, my question, what is that maximum height when the snowball is right there? That's the question that we're going to be answering. It doesn't matter what question you're trying to answer. You're always going to take the exact same steps. And as long as you can understand each step in the system that we're using, you're going to be okay. So we're going to take this picture and we're going to just completely consider the two moments at hand. Okay, so we are interested in the amount of time it takes the snowball to get from here up to here. So this here is going to be my initial moment, and if I want to jot that up on top, I certainly can. This is the initial moment in time, and for this particular problem, this is the final moment in time because that's the question. So the first step is to identify the variables. Just write them down. Don't worry about what they are. Just take it step by step. Remember, if you're driving to the grocery store and it's pitch black outside, your parents have to go to the grocery store, you have to go to the grocery store, and you're sitting in their car, you can't see the grocery store. You may turn on the headlights, but you can only see 50 feet in front of you. You can't see the grocery store, and you're never going to see it until you start moving. So even if you don't know where to go, you can either sit frozen in panic, which isn't going to get you anywhere, or you can take the first steps. I want you to write all of the variables under that initial moment. Under that initial moment, you have your position, your initial x and your initial y. You have your initial velocities, your initial velocity in the x direction, and you have your initial velocity in the y direction. At your final moment over here, and I'm just going to spread them out a little bit, you have your final x value, you have your initial your final y value, you have your final v velocity, x velocity, and your final y velocity. In between this moment and this moment, we have constant acceleration in the x direction, and we have constant acceleration in the y direction. If that acceleration wasn't constant, we would not be able to use the kinematic equations, and that would turn it into a calculus problem really fast. Also, there is amount of time that we're talking about between here and here, and the amount of time it takes to get in between this moment and this moment. That is what we're looking for. So we're going to put a big fat question mark in where what we're looking for. Now we're going to take each variable at a time. When we talk about the position, well, we can't talk about a position until we have a coordinate axis. I'm choosing to put the coordinate axis right here, right where that snowball starts. So basically I'm saying that at this point right here, my x value is going to equal 0 and my y value is going to equal 0. Well, that just happens to be the x and y position in the beginning. So my initial x value is 0. My initial y value is 0. That's how I set it up. Now I'm not even going to put units here because remember we're not even working with numbers. Well, I'll put units. No, I won't. I'm not going to put units because I don't want us to get those units confused with variables. So here my position is 0, 0 because I said I want it to be. All right. Now here at this moment, we don't know if this is our final moment for this particular question. We don't know what that final y position is at the peak. We don't know it. We may know it down the road, but we don't know it right now. And we don't know what that final x value is. We have no idea at this time where that snowball is. Be okay with that. Just keep moving forward. As far as final x velocity is concerned, well, I don't know what that is, but I do know it's going to be exactly the as the initial x velocity because that's one of the rules of projectile motion. That x, there is absolutely no acceleration in that x direction. None. There's no force. That snowball doesn't have a little motor on the back of it. So the acceleration in the x direction is going to be 0. We absolutely have to keep everything in the x and y axes completely separate from one another. The acceleration in the y direction is going to be negative g. That's when we use numbers, that's approximately negative 9.8 meters per second squared. But we're just sticking with variables here. That value is called g. And it's going to be negative g. The reason that acceleration is negative g because the Earth pulls everything down. And we're defining y positive to be up. So if everything's coming down and positive is up, then it has to be negative. It's going against what we had set out. Now here comes the questions. I don't know my initial velocity in the x direction or my initial velocity in the y direction. That's okay because we do know the initial velocity. Now what I'm going to do is I'm going to bring this down here just so we have a little bit more room to work. So we're taking, you could consider it a little sidebar. This is the same exact vector that's up here defining that initial velocity of the snowball, but I pop this out, I bring it down here. We cannot use angled vectors. I call them rebel vectors, rebel velocities. We need to break this vector down into its x and y component and only use those x and y components. I know that in place of this initial velocity, I can use its x velocity plus its y velocity, and that will be exactly the same thing. Well, this velocity and this velocity added together are the same thing as this initial velocity. Why are we doing this? Reminder, we cannot use angled vectors. We only have equations in the x direction and the y direction. So here, I know the angle between the ground, the horizontal, and my initial velocity is theta. Well, now's where we use SOHCAHTOA. If you need a little refresher with that, I do have a video. So I'm just going to assume you can use SOHCAHTOA and check out that video using SOHCAHTOA and breaking down vectors if you want more on that. All right, there we go. It's as simple as that. Okay, now let's go over here. We have some variables we didn't fill out yet. Well, look at this. I said before I didn't know what the final velocity is. And again, final just means the moment under consideration. It doesn't mean when the snowball is slapped up against this little boy's face, okay? It means what is the velocity at the final moment. Our final moment's when it's at its maximum. Well, the final velocity in the x direction, because we have zero acceleration, is going to be exactly the same as the initial velocity. Okay, so we're just going to get rid of this here because we've already taken care of that. And I'm going to take this and put it over here because it's exactly the same thing. It truly is like doing a puzzle, filling in those missing pieces. Here's the clue. You do the same exact thing for every single projectile motion problem, no matter what the question is. Notice we haven't even gotten to the time yet in solving that. We put it in as a question mark, but we do the same exact thing every single time. The final velocity in the y direction, well, that snowball at the maximum height, it is no longer traveling upward. It basically went up, 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 down, 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 down. And at the maximum point is that transition point. So the velocity at that moment will be 0 meters per second. So again, I don't know that final position at all. I'm going to leave lines there just to let myself know I've acknowledged those. I'm going to be okay with that. I'm going to move on to our kinematic equations. We have 3 of them that we work with. Now you may be saying, Ms. First, you just told me that there were only 3 equations, but you just wrote down 6. Well, if you look, they really are the same equations. Now let's differentiate them. These 3 equations we're going to use for our x values, everything happening horizontally. So we're going to distinguish the x's. Okay, we're going to put little x's by everything. Now notice too, I didn't put little f's for final. If there is not a little o representing the initial, original values, we're just going to know that they're finals. That just saves us, that just conserves us a few subscripts. Here I'm going to differentiate my velocities as being the velocities in the y direction. The only thing that's the same between these 2 equations is the time. So now comes the task of deciding on an equation. Oh no, which equation do I pick? Well, relax, okay? Just relax. Listen, we're going to take these, we're going to put them up there. We're going to determine it using the process of elimination. So what we're looking for ultimately is time. Well, neither of these 2 equations have the time. So we're just going to not even consider those. Those are not going to work out for us. Not today anyway. And let's see what else we have. Let's see. We'll start here with this equation. I don't know my final x position. I don't know it. I know my initial x position. I know my initial velocity in the x, see, because I can just look up here and find out. I don't know time, but I'm trying to solve for it. This is nice here because acceleration in the x direction is just 0, so this whole term is just going to cancel right out, and that will just leave us with this equation right here. And time is what I'm solving for. 2 unknowns. Let me just keep that in mind. If I have 2 unknowns, unless I have 2 equations, which I do sometimes, but in this case we'll just see how that plays out. We know that velocity in the x direction. We know the initial velocity in the x direction. The acceleration in the x direction is 0, so that entire term is going to cancel right out, leaving us with final x is equal to initial x. Look at this. We already knew that. So that's not very, this equation is not very helpful to us. It already gives us something that we knew. Now let's take a look at this equation over here. Let's see. Final y position. Oh, I don't know that. Initial y position, I know. That's 0. Velocity in the initial velocity in the y direction, I do know that. Time is what I'm looking for. And I do have the acceleration in the y direction. Again, here I have two unknowns. I don't know. It's not looking very good. At this point I could get nervous and panic and cry, or take a deep breath and say, hey, I still have one more equation. Let's see. Velocity, the final velocity in the y direction, I do know that. That's 0. Initial velocity in the y direction, I do know that. I know my acceleration in the y direction, and I'm looking for time. Woohoo! Now's when we celebrate. We found one equation and one unknown, and there is the winner. So we do a little happy dance. If you're not in a place where you can do a happy dance without looking like you're crazy, then just do it in your head. We always have to celebrate the little moments, because the better we feel, the more confident we feel, and the more successful we will be. And that is something that'll serve you well in physics or anything else. So now all we're going to do is we're going to plug in our unknowns. So the final velocity in the y direction is 0. See that? I'm just taking these values and I'm plugging them in. Remember, when I rewrote these equations, I just left off the little f's. The initial velocity in the y direction is v0 sine theta. All I'm doing, this is not physics, this is basic algebra, where I'm taking my values that I know and I'm plugging them in. Acceleration in the y direction is negative g, and time is what we're looking for. So now we're going to solve for time, because that was the question we're dealing with. The fact is, this works for anything. The system works for anything. So even if you're doing a different problem, you can use this video. If I want to get t alone, now this is algebra right here. I'm going to subtract v0 sine theta. Doesn't matter what this is. Don't get scared because it's variables. Okay? You're just going, so I subtract this from both sides. You're going to treat them just like you would numbers. And right now, t is being multiplied by negative g, so I'm going to divide both sides by negative g. And I find out that t is equal to v0 sine theta over g. Dun, 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 dun. Okay, good thing I'm tone deaf, or that could have been pulled for a copyright infringement. You may not even have known what I was singing there. Okay, there we go. That's the answer. Questions? Comment below. Make it a great day.